As András mentioned, I'm going to talk about words and disambiguation in Hungarian using transformers. So I will start with the brief motivation of this work. And well, naturally, there is an applicational part of the motivation. As it was also mentioned during the plenary talk, from natural language processing perspective, it's an important task or an important issue that we want to be able to distinguish between the different senses of words. So, for instance, if a sentence contains words like parliament, does this word refer to an actual physical location, or maybe a more metaphorical sense, like the organization who makes a decision and stuff like that. So there is definitely this application-oriented motivation for that. And there are a bunch of senses, bunch of possible senses of words. So if you think of the English WordNet, it has more than 100,000 different senses included in it. And making training data, annotated training data, is really cumbersome, really pricey, and really time-consuming thing to do. So the basic question is if maybe we can skip that very expensive and very time-consuming part and build a words and disambiguation system which is trained on language 1, very conveniently maybe English, and evaluate it and use it on language 2 without seeing any sort of words and disambiguated training data on this other language. Well, this would be Hungarian in our case. As methodological motivation, there is this cognitive gap, I would say, that even though these vectorial word representations are delivering really nice and really state-of-the-art results, and they perform very convincingly most of the time, but there seems to be a misconnection to the human cognition part of to the human cognition, in which people are, let's put it that way, are making associations to a very few properties with respect to the words and the concepts that they are talking to, as opposed to these vectorial representations, which are containing non-zero values everywhere. It's to put it in a metaphor, as if it means that if it was true also for humans as well, it would mean that also humans could describe every single concept from every single property aspect, which is clearly not the case, as it was shown by various feature norming studies earlier. Okay, so these are the basic concepts for word representations that we are all familiar with at a high level. So we are transforming the one-hot representations of word indices basically into continuous vectors traditionally. And what we are proposing here, or what has been proposed earlier, is to use such vectors that are not as sparse as being one-hot, not as extremely sparse as being one-hot vectors for indicating a single vocabulary entry, but also not as dense as the traditional embeddings are, but somewhere in between, where there are plenty of zero coordinates and a few non-zeros as well. This can be framed as a matrix decomposition problem, where we are basically have the original dense word embeddings that we trained with any of our favorite algorithm for that, and we are decomposing it into a product of two matrices. One of them can be, the matrix D can be thought of as a dictionary matrix that describes the semantic prototypes or the features, and the matrix alpha is such a matrix which tells us for each and every word which semantic atom or semantic property should be utilized in the reconstruction of the particular dense counterpart, dense representation of the very same word. And this kind of approaches have been proposed earlier. So I would like to put the whole framework into a bit of a context. Of course, there are those static word representations, the static dense word representations, which are almost nearly 10 years old by now. Then there have been their extension to the kind of in the kind of direction that I was talking earlier, so making them sparser. And of course, most recently there are these contextualized word representations, but until very recently, the two kind of extensions of the traditional static word representations have not been investigated. But in one of our previous work, we did something similar. So what this work is different from our earlier work is that in this particular work, we investigate the sparse contextualized word representations from the cross-linguality perspective, from an additional perspective of cross-linguality. Okay, so basically what I'm going to tell you briefly is in the upcoming few minutes is our earlier work, which was aiming at these contextualized sparsity without the multilinguality. And after I introduce this previous work, I will share with you its extension to the cross-lingual evaluation. So basically, we need a corpus. We run any of the whichever BERT model that we would like to. We stack these contextualized embeddings into a matrix X, and then we do the traditional matrix decomposition as if this matrix X would contain standard static embeddings. And during test time, of course, that's the more challenging part in this setting. We are relying on the dictionary matrix D that we were obtaining from our training data, and we are on the fly during test time. We are calculating the alpha sparse coefficients for each and every word formed within a sentence by fixing down the dictionary matrix D obtained during the training procedure, and that way our sparse representations would also become contextualized, because the embeddings themselves would come from a contextualized model during test time with the dictionary matrix D being fixed. Okay, and for figuring out the correct sense or correct feature or property of a word, we also construct an affinity matrix phi that was introduced on the previous slide. And by simply taking the dot product of a sparse word representation and this affinity matrix phi would and taking the argmax of this product would very conveniently tell us the kind of properties that our model would say that a particular word has. So very importantly, each and every column of this matrix phi, the construction of which I will tell you in a moment, can be directly connected to some human interpretable property or concept of some word. Okay, so let me introduce briefly the whole framework. So let's assume we have some sense annotated, so word sense disambiguated training data, which maybe tells us which particular WordNet scene set does a particular word in a particular context belongs to. We can frame this, or we can express this property of the word as a one-hot embedding. Then we can also obtain by the previously mentioned procedure a sparse representation for that word in the given context. By taking the outer product of these two characterizations of the particular word in the particular context, we would obtain this rank one matrix that we can stack up or sum up or aggregate for all the annotated words in our training data. And finally, if we add these matrices up, then we can do some post-processing. Okay, I just say some post-processing, but actually these are very important post-processings, but actually, so not the real focus of this work. So it turns out if you are not doing these post-processing steps, then the results would degrade severely. But so let me just put it briefly that we calculated these normalized positive PME values from the aggregated matrices that we obtained in the previously described manner. So now I'm changing my topic to the experimental settings, and actually these experimental settings is from our previous work. I'm just going to show you those modifications in our experimental settings that we made. So our earlier work was purely focusing on English. So for that reason, it was okay for us to use the BERT large case model, for instance, and we made a more systematic hyperparameter tuning or hyperparameter search. But as for now, we just went for the best combination, which was the largest amount of dimensionality for the sparse vectors. And of course, we had to change the transformer models to some model which handle multilinguality. It was because many of the talks were involving contextualized models, particularly tailored for Hungarian. I would like to emphasize that in our case, using, for instance, Hubert would not be a good way, because our training data for the Versen's disaggregated training data was still in English. So it was important that we had to use such a transformer model, which was capable of handling both Hungarian and English, for which we have the annotated training data. And yeah, actually we also kept the evaluation part on English so that we could measure the amount of negative effect or presumably negative effect that came with replacing the English transformer model with a more general purpose one, multilingual BERT and XML Roberta. As a baseline, we used a very simple nearest neighbor classifier for making predictions about the senses of words. So if we just take or use all the sense annotated embeddings for words with a given sense ID, we can, for a test case or a test for an ambiguous test case, we could just calculate the contextualized embedding or contextualized representation for that particular test word in its test context, and find its nearest neighbor among the training examples, and simply say that the correct word sense of that test word is the same as its nearest neighbor from the training data. In that case, we would say that this is the financial institution kind of sense for bank. But we wanted to test it in Hungarian, so I will briefly tell about the Hungarian dataset, which was the WSD dataset. It's a very tiny dataset, so we had the same kind of problem. We faced the same kind of problem that was mentioned in some of the earlier talks, namely that the evaluation in Hungarian was a difficult one. So this rather tiny word sense disambiguated dataset contains roughly 12,000 occurrences of 39 ambiguous words, and these 39 ambiguous words have roughly 200 distinct senses. So roughly speaking, one word can, on average, one word has 5 distinct meanings, but of course the distribution is rather skewed. So one possible sentence from this data set would look like this: az üzleti életben a megfontoltság komoly erény, which would be something like in business life, being prudent is a very big plus. And in this context, the life is annotated as having the meaning of being some form of an activity. And if this Berend disaggregated dataset would have a direct one-to-one correspondence to the English Princeton WordNet synsets, then we would have a very simple life, and we could just simply report accuracy or F1 score if this particular gold standard meaning had a direct correspondent in the English WordNet. But unfortunately, it was not the case for all the senses in the Hungarian corpus, and we contacted the authors of the WSD dataset, and they confirmed that it is such a mapping is not possible to be constructed. So what our system did is that made ranked predictions towards all the WordNet synsets, which, as I mentioned earlier, has more than 100,000 entries. And we were making sort of a hack out of with respect to the evaluation. So we find the nearest neighbor of every test sentence or every test ambiguous word, and for measuring the similarity to another sentence containing the same ambiguous words, we measured this so-called ranking bias overlap, which can give you similarity between two ranks. There would have been other ways probably to calculate this similarity, but okay, we can discuss it maybe during the questions. And the way we evaluated the quality of these rankings basically is that we measured the fraction of times when the most similar sentence, according to this RBO metric, was annotated with the same sense, the same Hungarian label that the particular query sentence, the particular query word is annotated with. And here are our results, which I show you briefly. So from left to right, the models have increasing size, and the larger the model is, the better. And for the largest model, which is the XLM Roberta large, we can see that the kind of LMMS approach with the prefix S at the beginning, which exploits this sparsity, had the best result. And I know I'm running out of time, but I'm also concluding my talk. So our results have confirmed our initial hopes that it's possible to build such cross-lingual models that see absolutely no training data on the target language for a particular task, in this case, words on disambiguation. And we hope that we also managed to show that sparsity can be beneficial in this context as well. And with that, I have one extra thing to tell you, that there is this demo where you can where you can see our predictions on the fly for any sentence that you type in. So thank you.